quantum physics and classic physics. Remember, you live in an incredible time when science itself is divided into two schools. There are the physics of big stuff like us and chairs and buildings and the universe, planets. But on the fundamental level of that, in quantum physics, the very small level, there's another set of rules that governs how the very small works. So if you didn't realize that last week, that's kind of the basic idea of what we were saying. And right now, the two they operate by different rules. Intuitively, they don't make sense. And incredibly, that's just where science is right now. They're still trying to figure out a theory that would bring the two together. Einstein was convinced that quantum physics was incomplete. He didn't think it was wrong. He just thought there's got to be something more here because he felt like you can't have these two worlds. That was in the 1920s, 1930s. Here we are almost 100 years later. We still haven't figured it out. Yes. 1920s and 30s is when they really began to unpack quantum physics and became aware of the very small. So to give you, just kind of to remind you, the first week we talked about science and religion, and I tried to make the point that there's really essentially not any conflict. They certainly study different ideas and different areas of study, but they're not necessarily opposed to one another. What you do get occasionally is a conflict that arises from a theological position called creationism or fundamentalism and materialism within science. So a scientist in their method studies what can be measured, the material world. Okay? That's their method. And they're limited to studying that. That's what science does. But occasionally you'll get a scientist who steps out of that world, keeps his white coat on, so he's speaking with the authority of a scientist, which is pretty big in our society. And he begins to talk about conclusions that are not limited to science, that are metaphysical, that are beyond the physical. So a scientist studies the world. If he steps outside of that and says as a scientist, there is no God, he's no longer acting as a scientist. All right? He's become a philosopher, but he's presenting himself as a scientist, and often they present it as though this is what science has proven, there is no God. It's just a mistake. It's just a confusion of roles. Science by design is materialistic, but when the scientist takes that materialism and tries to apply it to all of reality, that's where we get a conflict. Does that make sense? The same for the religious folk who take the story of Genesis and try to turn it into science. That was one of the problems with the design movement within theology. They were claiming that it was science, and it just was not science. So often the conflict that you hear about comes from the conflict between a very fundamentalistic view, which takes creation, the story of Genesis, as scientific truth, and a scientist who has taken the materialism of science and applied it to all of reality. We also made the point, though, that for centuries, a lot of the science was done by religious people. So they weren't historically in conflict. Talking about quantum physics, remember the three concepts, the three-legged stool of quantum physics, first being duality, that that truth, light, is both wave and particle. The idea that something can be two things at once. That truth is no longer limited to just the facts. That even science says the best way to understand light is to understand that it can be both. You don't choose one or the other, you understand it's both. And we related that to the idea of Jesus as divine and human. Hard to keep all that properly balanced and to think about it in the correct way. We usually err one way or the other. But indeed, we believe you come closest to the truth of Jesus by understanding that he was both. Okay? So, interestingly enough, quantum physics and theology sort of think in some of the same ways, is the point. Second leg of the stool in quantum physics was uncertainty. The idea that it sounds very simple, that a particle that you can measure its velocity or its location, but you can't measure both of them at the same time. Not because we don't have the right piece of equipment, but because you just cannot. You cannot do it. So there seems to be a veil sort of over reality, a limit to what we can know. That's what science tells us from quantum physics. Well, that sounds very much like what theologians say. We've been talking about how God is infinitely knowable. So there is always mystery further down the road to understand within theology, the same within science. Now, in the turn of the century, 19th, 20th century, scientists thought pretty soon they'd have it completely figured out. They thought, we'll be able to manipulate the world. There was one scientist, I forgot, fairly famous professor, who told students, I wouldn't go into physics. I mean, because we about done everything we need to do there. And that was in the late 19th century. It was this feeling that we will eventually know all there is to know. Now, you contrast that with then 30 years later in quantum physics, scientists have to say there's a limit to what we can know. So very much like a theologian who has to say there's a limit to what we can know. And then we also, and we're going to talk more about this with chaos theory, introduced the fact that there seems to be a certain level of chance within quantum physics. So fundamentally, at the fundamental level of the world, there is chance. And that was related to the fact that a particular particle in quantum physics has no specific location until it's measured. And prior to that, its location can only be stated as a range of possibilities or probabilities. Now, I know you're sitting there saying, wait a minute, this doesn't make any sense because the chair's there and it's made of particles. That's the problem. You're experiencing the problem. One world, the big world, works one way, but it's made up of particles that operate according to different rules. And we don't understand how that works yet. So the particles have a probability, a range of possible locations. It just introduces the possibility of chance within the world. And I think this is so important because I think most Christians think that God has I heard it on the radio coming out here. I listen to fairly conservative channels because I like the music. And they were talking about God has a specific plan for your life. It's all laid out. Just get on board, understand the plan, and let it go. That's a very common view. And there are people who would accuse me of heresy for raising the question. Quantum physics says that same God created a world in which there are probabilities, there are options, there are possibilities. Well, which is it? Is there some way in theology of bringing this together? And I think I think there is. I think that God created the world in this fashion because God wanted to bring forth as much diversity and novelty as possible. And this was the way to do it, to allow things to take their own course. We're going to say a little more about that with chaos theory. All right, that's kind of where we've been. Oh, and entanglement. Remember the idea that two particles related, separated by great distances, even by the width of the universe, and somehow they remain related. So all of a sudden, Paul's talking about the body of Christ and how we're all one part. We're parts of one body. We're all interrelated. You know, if God created a universe in which particles remain related, no matter how far they're apart, what does that say about? Okay, so again, there's this sort of congruence, this coming together now of at least quantum physics and theology. Okay. All right, so I hope to show you a video. I found a guy just this afternoon who explains this better than I do. But we got logged in, but I think there's still a problem getting it to actually show. I'm going to try one more time in a minute. Chaos theory, I told you, was emerging as one of the major areas of science, just like astronomy and biology and geology, and now there's chaos theory. Chaos theory is actually the study of order within the world, but order combined with chaos or randomness. How did it come about? It came about accidentally. There are two systems, there are lots of systems that are used to model chaos theory. One of them is boiling water. Do you ever wonder, you put water in a pan and it always boils in the same pattern. Eventually, it has a pattern to it. Where's that order come from? That's order, right? There's a pattern. There's a definite way that it boils. Why? Why didn't it just jump all around? Why does it boil the way it does? Another example of chaotic systems, as they're called, it's not that they're fully chaotic. There is order within the chaos. Another example is weather. We all know how difficult it is to predict the weather. Well, part of it is because it is what's known as a chaotic system, and chaos is defined as a system that is highly sensitive to initial conditions. So it makes it very hard to predict because just the slightest change in some of the initial conditions can make big differences in the end result. So it makes it very, very difficult to predict because you don't know all the initial conditions, because even the slightest difference can make a big difference down the road as the system unfolds. So the classic statement of particularly the weather as a chaotic system is called the butterfly effect. Have you heard of that? The idea was that a butterfly in South America could flap its wings and produce a tornado in Texas. And essentially it's true that weather is a system that is highly sensitive to initial conditions. That's why it's so difficult to predict. In fact, the fellow that I was going to show you, I'll still try in a minute, he says that after 7 days, a weather forecast on the 8th day is trying to forecast the weather. You might as well just average all the reports for that particular day since they started making reports, and you would be about as accurate as trying to look at what was going on with the weather and predict it. That 7 days is about the best they can do, and I would agree. It gets kind of sketchy on that 8th day. Even 7 is a little sketchy. And it's because weather is a system that's highly sensitive to initial conditions. So it's called a chaotic system. It's not that it's totally chaos, but that it's highly sensitive to initial conditions. Yeah, the spaghetti. Exactly, or yes, with hurricanes, exactly. That's what they're doing is they realize they can't, and so they're giving themselves a range of probabilities because they cannot predict it exactly.
Pick up a cow or a bus.
Right. Yeah, well, yes, which becomes part of then the initial conditions for what unfolds from there. So you've got all these conditions to try to know, and you can't know them all, and so you can't make that prediction. So the system seems chaotic, but it's not that it goes anywhere or everywhere. It's order within, there's chaos within order. So remember, the idea of what we're doing now, though, is that then we ask, if that's true, if that's the world we live in, that there are these chaotic systems, what does that say about God? Okay, so let me tell you how they discovered this, and maybe it'll help you understand. Edward Lorenz was studying weather years ago using a very primitive computer. And the computer printed out numbers on, looked kind of like a typewriter. And he was trying to develop models or formulas that they could use to predict weather. And he did, and we used them. But one day he was doing his runs on this computer, trying to see how the results worked and whether this, he had it was about 7 or 8 different factors like temperature and wind speed, and that he was trying to manipulate and understand how he could build some formulas that would accurately predict, given these characteristics, what the weather would be down the road. The computer was very slow, and he started it on a run and stopped it and then wanted to restart it. Instead of going all the way back to the beginning, he decided he would just enter the numbers that were printed and then let it run from there. What he knew, but he didn't think it mattered, was that inside the computer, it was using decimal points to the 6th or 7th place. But all that he entered when he restarted was to the 3rd place. So it's a very small difference. He didn't think it would matter. But it produced incredibly different results. Right? So, and he began to say, what's going on here? Well, this is where they came up with this idea of systems, such as weather, that are very sensitive to the initial conditions. By changing those numbers just a little bit, the computer produced a very different picture of the weather down the road. Okay, so all right. So you see why I don't think God has a specific plan. But it's not chaos either. All right, so let me see if. Well, I'll try it this way and we'll see.
You said even I would think
that.
Part of this video is sponsored by LastPass. More about LastPass at the end of the show. The butterfly effect is the idea that tiny causes, like a flap of a butterfly's wings in Brazil, can have huge effects, like setting off a tornado in Texas. Now that idea comes straight from the title of a scientific paper published nearly 50 years ago. And perhaps more than any other recent scientific concept, it has captured the public imagination. I mean, on IMDb, there is not one, but 61 different movies, TV episodes, and short films with butterfly effect in the title. not to mention prominent references in movies like Jurassic Park, or in songs, books, and memes. Oh, the memes. In pop culture, the butterfly effect has come to mean that even tiny, seemingly insignificant choices you make can have huge consequences later on in your life. And I think the reason people are so fascinated by the butterfly effect is because it gets at a fundamental question, which is, how well can we predict the future? Now, the goal of this video is to answer that question by examining the science behind the butterfly effect. So if you go back to the late 1600s, after Isaac Newton had come up with his laws of motion and universal gravitation, everything seemed predictable. I mean, we could explain the motions of all the planets and moons, we could predict eclipses and the appearances of comets with pinpoint accuracy centuries in advance. French physicist Pierre-Simon Laplace summed it up in a famous thought experiment. He imagined a super intelligent being, now called Laplace's demon, that knew everything about the current state of the universe, the positions and momenta of all the particles and how they interact. If this intellect were vast enough to submit the data to analysis, he concluded, then the future, just like the past, would be present before its eyes. This is total determinism, the view that the future is already fixed, we just have to wait for it to manifest itself. I think if you've studied a bit of physics, this is the natural viewpoint to come away with. I mean, sure, there's Heisenberg's uncertainty principle from quantum mechanics, but that's on the scale of atoms, pretty insignificant on the scale of people. Virtually all the problems I studied were ones that could be solved analytically, like the motion of planets or falling objects or pendulums. And speaking of pendulums, I want to look at a case of a simple pendulum here to introduce an important representation of dynamical systems, which is phase space. So some people may be familiar with position time or velocity time graphs, but what if we wanted to make a 2D plot that represents every possible state of the pendulum, every possible thing it could do in one graph? Well, on the x-axis, we can plot the angle of the pendulum, and on the y-axis, its velocity. And this is what's called phase space. If the pendulum has friction, it will eventually slow down and stop. And this is shown in phase space by the inward spiral. The pendulum swings slower and less far each time. And it doesn't really matter what the initial conditions are. We know that the final state will be the pendulum at rest, hanging straight down. And from the graph, it looks like the system is attracted to the origin, that one fixed point. So this is called a fixed point attractor. Now, if the pendulum doesn't lose energy, well, it swings back and forth the same way each time. And in phase space, we get a loop. The pendulum is going fastest at the bottom, but the swing is in opposite directions as it goes back and forth. The closed loop tells us the motion is periodic and predictable. Anytime you see an image like this in phase space, you know that the system regularly repeats. We can swing the pendulum with different amplitudes, but the picture in phase space is very similar, just a different sized loop. Now, an important thing to note is that the curves never cross in phase space, and that's because each point uniquely identifies the complete state of the system, and that state has only one future. So once you've defined the initial state, the entire future is determined. Now, the pendulum can be well understood using Newtonian physics, but Newton himself was aware of problems that did not submit to his equations so easily, particularly the three-body problem. So calculating the motion of the Earth around the sun was simple enough with just those two bodies. But add in one more, say the moon, and it became virtually impossible. Newton told his friend Halley that the theory of the motions of the moon made his head ache and kept him awake so often that he would think of it no more. The problem, as would become clear to Henri Poincaré 200 years later, was that there was no simple solution to the three-body problem. Poincaré had glimpsed what later became known as chaos.
Boost by Kroger Plus is more than worth it. With 2 times fuel points and free delivery for as low as $59 per year, you can save up to $650 annually. Try Boost free for 30 days. Kroger, fresh for everyone.
Hyundai Palisade versus Toyota Highlander. Look what Palisade has, and what Highlander doesn't. Hyundai Palisade.
I can't get the cursor to appear. We can worry about quantum physics if we can get the computer to work right here.
See it on the screen.
Yeah. Yeah, unfortunately.
chaos really came into focus in the 1960s when meteorologist Ed Lorenz tried to make a basic computer simulation of the Earth's atmosphere. He had 12 equations and 12 variables, things like temperature, pressure, humidity, and so on. And the computer would print out each time step as a row of 12 numbers, so you could watch how they evolved over time. Now, the breakthrough came when Lorenz wanted to redo a run, but as a shortcut, he entered the numbers from halfway through a previous printout, and then he set the computer calculating. He went off to get some coffee, and when he came back and saw the results, Lorenz was stunned. The new run followed the old one for a short while, but then it diverged. And pretty soon it was describing a totally different state of the atmosphere. I mean, totally different weather. Lorenz's first thought, of course, was that the computer had broken. Maybe a vacuum tube had blown, but none had. The real reason for the difference came down to the fact the printer rounded to 3 decimal places, whereas the computer calculated with 6. So when he entered those initial conditions, the difference of less than 1 part in 1,000 created totally different weather just a short time into the future. Now, Lorenz tried simplifying his equations and then simplifying them some more, down to just 3 equations and 3 variables, which represented a toy model of convection, essentially a 2D slice of the atmosphere, heated at the bottom and cooled at the top. But again, he got the same type of behavior. If he changed the numbers just a tiny bit, the results diverged dramatically. Lorenz's system displayed what's become known as sensitive dependence on initial conditions, which is the hallmark of chaos. Now, since Lorenz was working with 3 variables, we can plot the phase space of his system in 3 dimensions. We can pick any point as our initial state and watch how it evolves. Does our point move toward a fixed attractor or a repeating loop? It doesn't seem to. In truth, our system will never revisit the same exact state again. Here, I actually started with 3 closely spaced initial states, and they've been evolving together so far, but now they're starting to diverge. From being arbitrarily close together, they end up on totally different trajectories. This is sensitive dependence on initial conditions in action. Now, I should point out that there is nothing random at all about this system of equations. It's completely deterministic, just like the pendulum. So if you could input exactly the same initial conditions, you would get exactly the same result. The problem is, unlike the pendulum, this system is chaotic. So any difference in initial conditions, no matter how tiny, will be amplified to a totally different final state. It seems like a paradox, but this system is both deterministic and unpredictable. Because in practice, you could never know the initial conditions with perfect accuracy, and I'm talking infinite decimal places. But the result suggests why even today with huge supercomputers, it's so hard to forecast the weather more than a week in advance. In fact, studies have shown that by the 8th day of a long-range forecast, the prediction is less accurate than if you just took the historical average conditions for that day. And knowing about chaos, meteorologists no longer make just a single forecast. Instead, they make ensemble forecasts, varying initial conditions and model parameters to create a set of predictions. Now, far from being the exception to the rule, chaotic systems have been turning up everywhere. The double pendulum, just 2 simple pendulums connected together, is chaotic. Here, 2 double pendulums have been released simultaneously with almost the same initial conditions. But no matter how hard you try, you could never release a double pendulum and make it behave the same way twice. Its motion will forever be unpredictable. You might think that chaos always requires a lot of energy, or irregular motions, but this system of 5 fidget spinners with repelling magnets in each of their arms is chaotic too. At first glance, the system seems to repeat regularly, but if you watch more closely, you'll notice some strange motions. A spinner suddenly flips the other way. Even our solar system is not predictable. A study simulating our solar system for 100 million years into the future found its behavior as a whole to be chaotic, with a characteristic time of about 4 million years. That means within, say, 10 or 15 million years, some planets or moons may have collided or been flung out of the solar system entirely. The very system we think of as the model of order is unpredictable on even modest timescales. So how well can we predict the future? Not very well at all, at least when it comes to chaotic systems. The further into the future you try to predict, the harder it becomes. and past a certain point, predictions are no better than guesses. The same is true when looking into the past of chaotic systems and trying to identify initial causes. I think of it kind of like a fog that sets in the further we try to look into the future or into the past. Chaos puts fundamental limits on what we can know about the future of systems and what we can say about their past. But there is a silver lining. Let's look again at the phase space of Lorenz's equations. If we start with a whole bunch of different initial conditions and watch them evolve, initially the motion is messy. But soon all the points have moved towards or onto an object. The object, coincidentally, looks a bit like a butterfly. It is the attractor. For a large range of initial conditions, the system evolves into a state on this attractor. Now remember, all the paths traced out here never cross, and they never connect to form a loop. If they did, then they would continue on that loop forever, and the behavior would be periodic and predictable. So each path here is actually an infinite curve in a finite space. But how is that possible? Fractals, but that's a story for another video. This particular attractor is called the Lorenz attractor, probably the most famous example of a chaotic attractor, though many others have been found for other systems of equations. Now, if people have heard anything about the butterfly effect, it's usually about how tiny causes make the future unpredictable. But the science behind the butterfly effect also reveals a deep and beautiful structure underlying the dynamics, one that can provide useful insights into the behavior of a system. So you can't predict how any individual state will evolve, but you can say how a collection of states evolves. And at least in the case of Lorenz's equations, they take the shape of a butterfly. Hey, this part of the video is sponsored by LastPass.
How'd they predict how to get hitting the moon again with the thing they set up ready? Whenever they landed last week, before last.
Well, they probably used, I would guess, some of Newton's formulas, and that would be, see, they're not saying that everything is a chaotic system. There are systems that are non-chaotic and can be predicted. So I would, based on, say that's an example of a system that can be predicted. So if you remember the butterfly, the sort of circular pattern of a chaotic system, if you noticed, it never goes out of a particular area. So in one sense, you can say it's chaos, but it's not just like everywhere. It's within, or another way of saying that was, he says the formulas are deterministic, but the results are chaotic. The line that it traces will never repeat itself, but it'll never go outside that sort of box. Okay? So it's not, I know I do I want it to be one or the other, but what we're coming to understand about the world is it seems to be kind of like, is it wave or particle? Well, it's chaos and order combined. So it pushed me to look again at, let's see if my computer's going to. The computer really doesn't like what I'm asking it to do. There we go. When you think theologically about this, and you look at the story of Genesis, in the story of Genesis, so God's Spirit hovered over the formless void. So I've always tended to see the formless void as a way of talking about chaos, and that God brings order. God says, let there be light. Let there be the firmament. Let there be. We know, for instance, that our creation story in Genesis comes from other cultures. Do you know that? Doesn't look like it. Okay. The story in Genesis we found in other cultures, but it's different in other cultures. In the Middle East. Other societies in the Middle East had very similar stories, but in all of those stories, there's violence. So the god so-and-so slays the god so-and-so, and from the carcass of god so-and-so brings forth the world. So the world comes forth through violence and through a conflict.
So the difference might be that God spoke the universe in existence, and those gods tried to do it by some action or something.
Fighting, yeah. Whereas, see, all right, so you hear me say it came from other cultures, and you're thinking, oh, you mean like, okay, so it's like everybody. No, incredibly, they did borrow the stories, but they changed them. In their understanding of creation, God doesn't fight with chaos. In fact, God, in some sense, uses chaos to create the order. You may not agree with me, but from Genesis, can you see? So the Spirit of God moves over the formless void, and from that formless void comes creation. But there's no fight. But I often have thought of chaos as opposing God. But when I go back now and look at Genesis, it doesn't say that. It just says there was a formless void, and God's Spirit hovered over that, and God spoke, and spoke it into, and in other words, there's no battle, there's no conflict, just God introduces order into the formless void. So what gets me excited is that we finally reached a point now with chaos theory where we're discovering that maybe chaos isn't an enemy, but is somehow with order. So there's chaos and order in the world, and that the combination of the two is creative. Just as our Genesis story tells us it is. I mean, so I find a congruence between the scripture when I now go back with glasses that are reading the text and not reading into the text. By looking at nature and what science is telling me, I now see something about God that's been there all along, but I missed. Does that make sense? Another way of using this information to think theologically is, so he mentioned that the spirals are confined in that box that he called a strange attractor. So think of your life this way. What if, as a person of faith, Jesus is your strange attractor? That your commitment to faith holds you within this box. But within that box, your life takes all sorts of paths, makes all sorts of turns and curves. But as a person of faith, you're always in that box. To me, that's extraordinarily helpful because when I think about it, that's pretty much the way my life seems. You know, it is sure not a straight line. And it's sure not repeating. It's different every day. And yet, I understand that life within the frame of faith, within the strange attractor that I'm identifying as Jesus. Okay, so, it kind of, makes sense to me. And so then we begin to answer the question. I'm not going to probably get to that tonight. Well, I might. So I posed the question maybe early on about evil in the world. Well, if it's a world in which God decides every moment and every step and it's that straight line, then I have to say God's responsible for the evil. But if it's a life lived within the strange attractor and there's a measure of freedom, then maybe I'm not quite sure what the source of evil is, but there's room for evil in that system. That isn't a denial of God. I'm still in relationship with the strange attractor, but indeed it can be experienced as evil. So anyway, that's kind of what I'm I'm playing with in my mind. And that, to me, helps me sit easier with God. All right, so then the next question is, if you look at Scripture, I think that's what I see in Scripture. We've been hearing the Joseph story in evening prayer. There's all kinds of chaos within that, and yet it's within a frame that makes sense and is faithful. There is a plan that was unfolding, or order that was unfolding, that was identified only when they looked back. But so, and I think that happens a lot in Scripture, where there seems to be a partnership from God and humans, but it's not a straight line. You know, why did the Israelites wander for 40 years before they got to the Promised Land? What the heck was going on? Did God make a mistake and choose the wrong people? No, I don't think so. I think it's this unfolding of order and chaos, of freedom and direction and determination. Okay, any rebuttals? Okay, so all right, so we're going to leave chaos theory, sort of, and talk about astronomy real quickly, okay? Are you all right? No, I throw a lot, well, anyway. Okay, so, you know, over the years, there have been several different models, and I'm not going to spend a lot of time on this. This is Ptolemy's model. He developed this in the first half of the 2nd century. It was highly influential all the way up till about the 17th century. It had Earth in the center, and everything moved around the Earth. Christians loved it because we are the center of God's world, are we not? Okay, well, and it was nice having the Earth in the center. And the way they thought about it was Christians saw all of this as a land of perfection, for that's where God lived. And that's why the planets orbited in perfect circles, because there was perfection where God was. And so the heavens must be perfect, and so orbits are circular, and the Earth is, of course, at the center of it all. Copernicus came along. He's the guy that came up with a model that's called the heliocentric model. He dared to put the sun in the center and put the Earth out here. This is the model that Galileo defended. It's not right. A lot of people think it was, but it's not. Because Copernicus, they were, you know, I don't know how these guys did it, but they would observe these things, and they were trying to explain what they saw. And to better explain what they saw, Copernicus had the planets orbiting within their orbit to try to explain what they were seeing. He was wrong about that, right? Remember, I told you that's part of the problem when Galileo was on trial. He was defending a system of science that the people in the church knew was not correct. They didn't agree with. Which brought us to Kepler's model. Kepler took Copernicus's insight that the sun was at the center, but realized by then that the orbits were eclipses, not perfect circles. By then, they had sort of gotten away from this idea that the heavens have to be perfect, because after all, Galileo and others had gotten out their telescopes and they'd seen the craters on the moon, and they were anything but perfect. I mean, literally, this is what changed their mind. They said, wait a minute, it is obviously not perfect up there. We can see, and it's not perfect. So that sort of freed things up a little bit, and in the midst of that, Kepler, who doesn't get as much credit as he should, comes up with a system that did away with the circular orbits and had the planets orbiting in an eclipse, and indeed that matched the observations. So, I shouldn't have, but so just to tell you quickly the story of how the universe came to be, and you know, Or I don't know if you know. You know now, we know that the universe is about 14 billion years old and that it had a beginning. Up until about 1950, it was assumed by scientists that the universe was static and had always existed. Now, think about that, 1950. That's pretty late. We thought the universe was just eternal. Theologians were over here going, it had a beginning. Genesis had a beginning. Scientists over here saying it's eternal. Okay. The idea of the Big Bang, a beginning for the universe, began to develop. It was called something else, but someone disparagingly referred to it as the Big Bang. Oh, he's talking about that stupid explosion that he says started the universe, and they started calling it the Big Bang, and it stuck. So we refer to it as the Big Bang. They said, if there was a Big Bang, if some kind of rapid expansion of the universe, there must be some energy. And they did some calculations. And they said, if the Big Bang's true, then anywhere you look in the universe, there ought to be some energy that's left. And it ought to be about 5 degrees Kelvin. Well, there were some scientists in, I think it was around 1950, somewhere in there, in the 50s, who were working on a different project with some very crude equipment. They had a satellite dish, and they couldn't get good readings from the satellite dish. And some scientists up the road said, check for pigeon poop. It's probably pigeon poop. And they went out there and they checked for pigeon poop, but it wasn't pigeon poop on the satellite dish. They kept getting these readings. And finally, they got in touch with some scientists way up the road who were trying to find this energy left from the Big Bang. And indeed, they discovered that what they were seeing that was bothering them was the energy left from the Big Bang. The temperature they measured was 2.7 Kelvin instead of 5, but it was close enough. Those of you who have had old television sets, you remember the static between channels? Some of that static was energy left from the creation of the universe. You were seeing it on your television set. We just didn't know what it was. That discovery of the energy was pretty much the key moment for the acceptance of the Big Bang Theory. So science did a complete, as they say, paradigm shift. And they went from believing that the universe was eternal to saying it had a beginning. Okay. Let me give you a little bit more. So it's about 14 years that it's been in this process, and they're fairly sure about that timing now, 14 billion years. It started in what they call a singularity, which was an incredibly dense point. I mean, it's hard to even. It wasn't really an explosion, but it was a rapid expansion that is often thought of as an explosion. All right, the only elements that existed in the early universe were helium and hydrogen. That presents a problem for us. You know why? Because we're made of carbon. There was no carbon in the universe initially. The expansion continues. That's kind of what this is depicting. So it starts here at a point and then begins expanding. And as it expanded, it cooled. And as it cooled, atoms began to form. And from the atoms, matter began to coalesce. And stars began to form. Okay? The stars ignited. As they became dense enough, they got hot enough to ignite, and fusion reactions were created within the stars, just like in our sun. And it's those stars that cooked the initial elements to form carbon and iron. We know now that in the lifetime of a star, it cooks the elements, and then at some point it runs out of energy and it explodes, a supernova, and forms a nebula. Our sun will do that someday. It's not good news for us, but it's a long ways off. But the suns explode, and when they explode, they spewed the heavy elements back out into the universe. Those heavy elements recoalesced into planets. And here we are. The Earth formed about 3 billion years ago with those heavy elements, and somehow or another life on Earth began not too long after that 3 billion year mark, not too long after the Earth was formed, and here we are. All right. Interestingly enough, Einstein back in the 1905, 1910, somewhere in there, when he was working on relativity, in his formulas, he discovered that the universe was expanding, and it's still expanding. But he didn't believe it. He thought he was wrong. And so he put in a figure in his formulas to adjust out the expansion. He called it his greatest mistake. He didn't trust his own formula. So it took Hubble in 1929 to prove and to discover that indeed the universe is expanding. And it's still expanding in all directions. So not out from the center, but everything is. Such that someday, way off in the future, the night sky will be black because everything will be too far away for light to ever reach us, because it's still expanding. It's generally believed now that the universe will expand indefinitely, eventually cooling, losing its energy, and sort of dying a long, cold death as it expends its energy. It's the second law of thermodynamics. Order takes energy to maintain, so we're burning energy to have all of this order, and eventually we'll run out. That ordered systems tend toward entropy, which is disorder, and the universe will eventually simply burn itself out. There was for a time a thought that it would recollapse, and that's not completely ruled out, but that's not I think that's not the common idea now. It's just that it will expand indefinitely. The expansion will slow, and it will eventually, further off than any of us can imagine, it'll cease to have life or energy. Okay. All right. So there's some good news to end on. But essentially, science and theology now are again, sort of like in quantum physics, thinking along the same lines, that the universe has a beginning and has an end. Is that not what Christians say? We agree now that it had a beginning, that it continues to change and evolve, that it's not static. We don't worry about it being perfect anymore. We know it also has an end. What we don't know in science is what existed before the singularity and what caused the expansion. Stephen Hawking, before his death, thought that he knew. He had a hypothesis, but no one has proven that. I've not seen anything that suggests they're on the verge of being able to say what existed before the singularity, before the universe began to expand.
Quick question.
Yes?
What about black holes?
I don't know much about black holes, because we don't know much about black holes. I mean, we know more than, but are they, entrance portal between worlds? I don't know. Do they eventually just gobble us all up and we never get out? I don't know. And I haven't seen any speculation that I thought was widely supported enough to begin to draw conclusions. I think there's still a mystery for the most part.
How do we refer to the area, the space between the physical matter and space? Like, is it like dark matter, or what is it? What is that? What's there? Is it a vacuum? Is there something there? What do you call that?
There's not. Originally, we thought that there was ether that filled. It was a substance called ether that filled space. But we now know, no, there's not something that fills space. I'm not sure that it's a perfect vacuum, but I guess that's probably a way of thinking about it.
So when they talk about dark matter,
Dark matter, kind of like black holes. We don't know much yet. Yeah. And what that might mean theologically, I don't know.
Well, I had a thought a while ago when you was talking about the moon had craters, so they knew it wasn't perfect out there. That might have been the perfect moon. I mean, who's to say it wasn't perfect?
Well, in their definition, perfect was perfect circles, and craters weren't perfect circles. So for them, that meant it wasn't perfect. Yeah, God. So, this is an aside, but in Genesis, when God's doing creation, several times God says, God saw it and said what? It's good.
yeah.
Think about that for a second. God didn't say it was perfect. God says, it's pretty damn good. That's, for a day's work, all right. I mean, that's going to be important later. God says, it's good. Indeed, after creation of humans, God says, it's very good. That's some good work. But God doesn't say in the text, it's perfect.
Well, my thought too, also on the Big Bang Theory, God spoke it and it happened, and that's Big Bang could have been what it took to make his command happen.
Well, exactly. For theologians, what was prior to the singularity, we think we know. I mean, we say, well, God, it's God. And that is the beginning of God's work of creation, is the expansion of the universe. So for us, not a big problem. And as you can see, there's not really a conflict there with science. Science has given us the best they can. Now, if they go beyond and say, well, there's no God. No, they can't. They don't know that. That's not a scientific statement. That's metaphysics. That's philosophy. And they shouldn't say that as a scientist. They can say it as an individual, but not as a scientific opinion. They're going beyond what they can say. But yeah, as we understand it, it's easy enough.
Camp McDowell, for instance, was one time covered with water, obviously, to make coal under it, which is sediment from a. That's just so hard to imagine.
Yes.
And big
Water.
hills and, yeah.
Yeah.
That's so much I don't understand, but they've proven that, obviously.
Oh, yeah. Yeah. Yeah, we'd be 20 feet under here, I think, or even further.
Yeah.
So let me push on just to give you one more piece of the puzzle. Occam's razor. This is This is kind of a rule in science. And the rule is simply this, that the simplest explanation is probably the correct one, the one that uses the least number of elements. Now, again, let me make my point here. This was a principle put forth by William of Ockham in the 13th century. William of Ockham was an English Franciscan monk. So again, this idea that science and religion are in conflict just isn't correct. He wrote a lot about philosophy, but he's most famous for what's called Occam's razor. The simplest explanation is probably the right one. Now, let me tell you quickly about the anthropic principles. This is science. There are, and you'll get different lists, some of them 10, some of them 15 particular principles. I'm going to give you 3 of them here. 15 is one of the numbers. People expand and contract the list depending on how they apply the idea. But this is science. Science tells us that there are certain settings in the universe that if they were slightly different, there would be no life as we know it. And all of these settings had to be set at the same time. It couldn't be that you do one and then it falls into the second. They all had to be there. To give you an example, the expansion rate of the universe, if it had been slightly different, the universe would have collapsed in the first second. Or it would have expanded so quickly that matter could never come together as stars. So the expansion rate had to be almost exactly what it happens to be. Okay? Another one is the force that holds atoms together, basically. If it were slightly stronger, it would have been too strong, slightly weaker, and atoms would have never come together. And then the third one that I'm going to mention, there were particles and antiparticles in the initial universe. And there happened to be one more particle for every antiparticle, if I'm saying that correctly. So it says there were 1 billion and 1 protons and 1 billion antiprotons, so to speak. And so 1 proton made it through and out. If it had been different by 1 proton, it would have annihilated itself in the beginning. So as I say, there are longer lists and shorter lists. For instance, some of the loose lists, I'd say things like the fact that the Earth is the exact distance from the sun that it needs to be. That's not on everybody's list of the anthropic principles. Some people say that's stretching it too far. But there are several things like these which leads theologians and scientists, Alistair McGrath is both, to write books like A Fine-Tuned Universe. Because so far, to their consternation, science cannot explain why this occurred. Now, what they do, though, is talk about multiverses. Scientists came up with this idea. They'll say, well, look, the universe isn't all that special. You're saying it's incredible that life exists and all these settings were just right for life. But guess what? There are hundreds of millions of universes out there. And with so many, it's no wonder that one of them happened to produce life. You get the argument? And that was really the beginning of the multiverse hypothesis, that there are all these other universes out there. And so it's no wonder that our universe happens to be right for carbon-based life. But one of the problems is they say we'll never be able to contact those other universes, so there's no way to prove this right or wrong. That's not science, you see. That's not science. That's philosophy. That's metaphysics. but they're making this case, and it's fascinating, and a lot of people talk about it, but I don't see it, okay? But this is how they respond. All right, now I'll end here. I'll just show this to you. There's a story about Bertrand Russell, who was the best-known philosopher in the 20th century. And he was talking with a man named Andre Lind, who teaches physics at Stanford University. He has an endowed chair at Stanford University. Teaches theoretical physics. And so they were together in a room, and Bertrand Russell asked him to explain the multiverse idea to him. And so as they do, Andre Lind went to the blackboard and started doing all the formulas to show Bertrand Russell, the philosopher, how you got to the idea of multiverse, okay? Bertrand Russell, when he finished, asked him, but how did you get that? And Andre Lind would go back to the board and say, well, yeah, it's these formulas. And they kept kind of missing each other. And Bertrand Russell tells the story that finally he stepped to the board and drew a white line around that. And he said, no, Andre, what I mean is, how do you get this? And this was the physics answer. You need God for that.
Multiverse, what do you call it? More universes. Isn't that the whole reason for that, is to deny
Yes,
unintelligent?
I think so.
Yeah, but I mean, but still, it's something from nothing. You know, the universe was made something from nothing. So when you get to those other universes, they had to come from somewhere. Somebody had to, you know.
Yes,
So,
and it
why
still,
they-
some people argue, it doesn't matter how many universes.
Right.
This one does exist and it's extraordinary.
Right.
And God created them all. I mean, you still haven't answered the question. There's a story about somebody asking a physicist about, no, the physicist asked a woman who asked him, I think the world is on the back of a turtle. And the physicist asked the woman, well, but what supports the turtle? And her response to the physicist was, it's turtles all the way down, honey. So with multiverses, you got the same problem. It just kind of hides the issue. It doesn't really answer it. It's still extraordinary that we're here, and there's still nothing that says you're not free to believe that it is from God. Here's what Einstein said. And Freeman Dyson, a major physicist, and this is something to think about on the way home. Barbara Brown Taylor puts it well, I think. She's right. You know, the Earth is spinning. The Earth is traveling around the sun. But a lot of people don't realize that the solar system itself is revolving in the galaxy. Yeah. And I think it's like 240 million years ago was the last time we were where we are now, as we evolve all the way around the galaxy. Now, I forgot to mention, they now estimate most galaxies have 200 billion stars. They now estimate there are 2 trillion galaxies in the universe. Big place. Okay, I need to let you go. Thank you for sticking with me. Next week, evolution, biology, the big E. Thank you all. Appreciate it.
We'll be ready for you. Yeah.
All right.